I'm 110H, Dr. Bevilacqua here. Homework 7, the reaction sheet. You guys have the answers to this. What I want to do is just go through a few representative examples from each class and give you some clues about how to think about this and what I do when I approach these problems. And often the first thing that I do is to eliminate species that aren't going to participate in the reaction. So let me show you. When I look at number 1, barium hydroxide, I recognize that as a soluble salt of hydroxide. I know it's a strong base. So I ask whether or not the barium and the chloride can interact with each other because they're both free. I know that they cannot. They're soluble, so I cross them out. And I'm left with hydroxide and H+, and I can immediately write down the classical archetypal reaction for a strong acid and a strong base. There's no need for 2s or anything in there. So that's an acid-base reaction. Let's look at a precipitation reaction. When I look at this, I ask about whether or not the cation and the anion can come together and interact with each other. Of course, sodium chloride cannot, so I can immediately go through and cross those guys out. Then I can look at barium and carbonate. I recognize those as being a precipitate. It's a good size match, large and large. It's a large charge coming together, and that's a precipitation. Let's take a look at another reaction. Let's say number 6 here. When I look at this guy, I recognize it immediately as a potential for dissolving in liquid water, and I know that calcium is near the top of the reaction series. When I look at it, it's the fourth one down, so it will react with liquid water, and when it does, it should form hydrogen and hydroxide, which turns the solution pink typically. However, this is a special one because nearly all hydroxides of metal ions are soluble with the exception of the +1 ions in barium, but this guy is insoluble, so I can write this as both a precipitation and a redox reaction. This is also a precipitation. Let's look for another one. Let's do a redox right here. Let's do both 7 and 8 together. They both have the potential for being redox, and so what I recognize is a solid metal, and then I recognize ions of a metal in solution. And then I just consult the activity series. Chromium is more easily oxidized. It's more active. It's already oxidized, so there's no reaction here. Number 8, I've also got a solid metal, and I've got ions. Aluminum is more easily oxidized. So this reaction will go, it gets oxidized, and the silver gets reduced, and I just make sure that I put my 3 in there so that my charge is balanced. Let's do a complexation reaction. When I look at number 9, what do I see? I've got potassium and nitrate. I know these guys are soluble because it already says AQ, and I just get rid of those because I know they don't interact with each other. And then I ask what happens between silver and cyanide. I think back to the copper penny demonstration, and silver and cyanide first came together to make a 1-to-1 complex. Because that guy's overall neutral, it precipitates out of solution, but then somewhat surprisingly, I add more salt and it goes back into solution, if you remember, and that's because it makes the complex ion, and then I get ion dipole interactions, which solubilizes this guy. Number 10 is a very similar type of thinking. The potassium and the nitrate are soluble. I get rid of those, and I recognize that as the gold chloride complexation reaction. Let's look for just a few more. When I look at 14, I recognize this as the potential for dissolving, again, a metal ion in an acid. And when I look at where zinc is, it's in a part of the periodic table where it's kind of on the edge of reacting in steam or reacting in acid, but this has a potential, because it's on that edge, it has a potential to react with a weak acid. It has enough driving force to break the bond, especially chlorous acid is not the weakest of the weak acids. HClO would be even weaker still. So it can kind of go in and dig that proton out and reduce the H plus down to H2, itself get oxidized, and in so doing it's going to liberate the chlorite ion. And so that's kind of the way the game is played. Let's see, let's just do one more kind of fancy one down here, which is number 22. When I look at this, I immediately recognize this as well, mercury is down well below H+, so it shouldn't dissolve in acid, just like copper shouldn't dissolve in acid. But this is a special acid. It's an oxidizing one. It's nitric acid, and this does the analogous reaction to what copper did, where the copper pennies dissolved in nitric acid. So I'll stop there, and hopefully by going through this, it gives you some idea on not the details of writing and balancing the reaction. I think you guys know how to do that. It's more seeing the reactants and knowing whether there's going to be a reaction or what type of reaction there's going to be. Thanks for listening, and thanks for watching.